So far then, we've established the eigenfunctions of Lz and Lx and Ly, since they must just be rotated versions of the Lz eigenfunctions. And we've just mathematically established the eigenfunctions of the L squared operator, the spherical harmonics. These spherical harmonics look fairly complicated mathematically. However, we can actually visualize them in a fairly straightforward fashion, mostly without doing any real calculations. To do that, we're going to step away from the quantum mechanical problem for the moment and think instead of the modes of vibration of a thin spherical shell. Now, we're not going to solve this problem, though it's actually fairly straightforward mathematically. If we were to solve that problem, we would find various different ways or modes in which this shell would vibrate. A mode of oscillation is one in which every part that's vibrating is vibrating at the same frequency. Essentially, those frequencies are the eigenvalues of this classical oscillation problem. Each of these possible modes of oscillation of the spherical shell has a different spherical harmonic as its solution. Now, let's just look at one example here. Here's our spherical shell, and one possible mode of oscillation, I'm showing you this nice smiley face on the front here, is that we're squeezing down on the poles and the equator's getting bigger and this goes in and out like that. And so we're able to see a kind of mode of oscillation of this particular spherical shell. We squeeze from the top and the equator gets larger, or we pull in from the top and the equator gets narrower. So in this case, the spherical harmonic is a function of the two angles, phi around the polar axis, sometimes called the azimuthal angle, and theta, the angle relative to the polar axis. In the case of the vibrations of a spherical shell, these spherical harmonics are the amplitudes of oscillation as a function of angle. As I said, one of them was that one where we're squeezing and stretching, squeezing from the top and it gets larger at the sides. There's also a breathing mode where the whole shell gets bigger and so on. The spherical harmonic in that case is the amplitude of this oscillation. It's positive perhaps in this direction and negative in that direction, or we can think of it the other way around, but it's the amplitude of the oscillation. So it could be, as I said, positive along the polar axis, and that would make it negative along the equatorial axis, or it could be the other way around. But it's the amplitude of the oscillation that's a spherical harmonic. This oscillation goes in and out in time, but the spherical harmonic is the amplitude of that oscillation. The only substantial mathematical difference between spherical harmonics we're going to be thinking about in quantum mechanics and the solutions to this classical problem is that the shell's vibrations must have real amplitudes. And so instead of complex functions, e to the I m phi, with positive and negative m for the variation round the polar axis, we use only positive m, but use both sine and cosine solutions for the phi variation. Since the solutions corresponding to sines and cosines around this axis are merely rotated 90 degrees with respect to one another around that axis, we only need to understand one of these to understand the nature of the spherical harmonics. It's simple to construct the e to the I m phi solution from these. So let's look at several of these spherical harmonics, first as vibration amplitudes for a spherical shell.
So here is our first oscillating mode for the spherical shell. This is called the breathing mode, and it corresponds to the shell just going in and out equally in all directions, all angles. And that means that the spherical harmonic, which is the amplitude of this oscillation, is simply a fixed sphere of unit amplitude, if we like, because all of these points are oscillating at the same amplitude independent of angle. And this one corresponds to L equals 0 and M equals 0. The next one we can look at is for L equals 1 and M equals 0. Now, I've indicated here a circle that goes round the middle of this sphere. It's not that this sphere is sliding up and down in here. It's really more like a balloon in which this circle is drawn on the surface of the balloon and it's staying fixed. And we're merely moving air, as it were, up and down inside the balloon. That would be one way to think about it. Now, this circle here is then a circle on which the amplitude of oscillation is 0. That means that this is what we could call a node of the oscillation, and we can refer to this then as a nodal circle. So the spherical harmonic corresponding to this oscillation then is something that is actually 0 for all of these angles. Up here it's positive, and if we choose it positive at the top, it's negative down here. So it's the amplitude of this oscillation. We can also go to L equals 1, M equals 1, and this is really the same oscillation as we just looked at, but rotated 90 degrees. We still have a nodal circle here, and we've rotated it from being an equatorial circle to being one that goes through the poles of this sphere. So like the North Pole and the South Pole, for example. Now, we're going to find this as a general behavior. L tells us the number of these nodal circles. And M tells us the number that go through the poles, North Pole, South Pole, of the sphere. Here's L equals 2, M equals 0. Because L is equal to 2, we must have 2 of these nodal circles. And because M is equal to 0, none of them go through the poles. So this is like what we were doing with a balloon, where we squeezed on the top and the bottom, and it moved out sideways. That was kind of like an L equals 2, M equals 0 mode. If we go to L equals 2, M equals 1, we still must have 2 nodal circles, one of which passes through the poles. So this is a vibration in which we have quadrants going in opposite directions relative to one another. So as these 2 quadrants go out, the other 2 go in, and the one round the back here. And again, when we go to L equals 2, M equals 2, this is really the same oscillation we were just looking at, only now we've rotated it round 90 degrees, and now both of these nodal circles go through the poles of the sphere. And again, we have adjacent quadrants oscillating in opposite directions from one another. So the spherical harmonic might be positive in this quadrant and that quadrant, but negative in the front one and negative in the back one, for example. So let's just summarize the rules we've been seeing for the spherical harmonics for a shell. Basically, using these rules, we can essentially draw out the spherical harmonic without doing any real calculations, at least for the qualitative behavior of it. The lowest solution, the L equals 0, M equals 0 solution, is simply this breathing mode. The spherical shell expands and contracts periodically, but uniformly in all directions. And that means the spherical harmonic is just a sphere. But for all other solutions, there are one or more of these what I've been calling nodal circles. That is, circles that are a node, a 0 of the oscillation on the sphere. So that means that a nodal circle is one that is unchanged in that particular oscillating mode. Everything else may be oscillating, but no point on the nodal circle is actually moving. Note the following rules for spherical shell modes. The surfaces on opposite sides of a nodal circle oscillate in opposite directions. The total number of nodal circles is equal to L. The number of nodal circles passing through the poles is M, and they divide the sphere equally in azimuthal angle phi. We saw that, for example, with the division of the sphere into quadrants if we had 2 nodal circles going through the poles. The remaining nodal circles are either equatorial, that is, round the middle of the sphere, or at least parallel to the equator. And these ones are symmetrically distributed between the top and bottom halves of the sphere.
To repeat, it's the amplitudes of these oscillations as a function of angle that are the spherical harmonics. The amplitude of the vibration at any given angle is the spherical harmonic function. Spherical harmonics are functions of angle only, not radius. Hence, for the angles corresponding to the nodal circles, the circles on the sphere where there's no oscillation, the spherical harmonic is 0. Note that the amplitude of the spherical harmonic may be positive for one range of angles and negative for another. For example, for all the L equals 1 spherical harmonics, the function might be positive on, say, the northern hemisphere and negative on the southern hemisphere.
We can also formally plot out the spherical harmonics on what we could call a parametric plot, where the distance from the centre at a given angle represents the magnitude of the amplitude of the spherical harmonic function. So, rather trivially, for the L equals 0, M equals 0 spherical harmonic, this parametric plot is just a sphere, because the spherical harmonic has an equal amplitude in every direction. For the L equals 1, M equals 0 spherical harmonic, now we have two lobes on this parametric plot, and they have opposite signs, so I've marked one as a plus and the other as a minus. So this really looks like two spheres, one on top of the other, but this one corresponds to positive amplitudes and this one to negative. And we can rotate this round in space just to get a clearer look at what this function actually looks like. Now, let's look at the L equals 2, M equals 0 one. This is the one that corresponded to what we were doing to the balloon when we squeezed it at the top and the bottom. So what happened at the top had the same sign as what happened at the bottom, and what happened in the middle had the opposite sign. Now, you'll note this function is pinched down towards 0 at two different circles of angle here. Those correspond to those two nodal circles on the sphere. These pinching in here. So let's look at what happens to this one as we rotate it round in space to see its shape. The L equals 2, M equals 1 spherical harmonic has positive lobes here and here and negative lobes here and here. This one corresponds to two nodal circles, one pinching in here in the middle, kind of like an elastic band round our balloon, pinching it in, and another one pinching it in this direction. This is the polar nodal circle, and this is the equatorial nodal circle. So let's see what happens to this one if we rotate it round in space to see its shape.